Hello, everyone. My name's Kelly Olson. I work for a company called Supranational. And today I'm going to be talking about hardware acceleration for Lurk and Nova, or how to make Lurk fast and cheap is really the goal of the talk. Just to give a quick background on Supranational, we're a company that develops a lot of open source cryptography, and we really focus on hardware acceleration of that cryptography. We've been long-term partners of the Protocol Labs ecosystem, have contributed to Filecoin, are currently contributing to Lurk. And these are some of the projects that maybe you've heard of or may be interested that we do. We have a library called Blast. It's a BLS 12381 signature library. This is used by Ethereum, Filecoin, Aptos, Sui, and others. We have a library called Spark. This is actually what underlies the GPU performance of Nova and Lurk itself. And this is just a general purpose library that enables you to accelerate a variety of curves and different proof systems. And then in addition to programming for off-the-shelf hardware like CPUs and GPUs, we actually develop custom silicon. So we're in the process of working with Protocol Labs to build a low latency ASIC for something called a verifiable delay function. And the verifiable piece of this delay function is actually instantiated using Nova. So we're creating the proofs for this delay function using the Nova proof system. So just to start off the talk, I think this is kind of a good, is a sort of good precedent for where we're at today in the SNARK ecosystem. So there was a paper about 25 years ago out of AT&T Labs where they are talking about basically data encryption in transit. And the author says, computers are fast enough that the overhead is barely, in some cases, tolerable. And I think that's basically where we're at today with SNARKs. It's hard to believe that this is how it was 25 years ago, but today, data in transit encryption is ubiquitous, on-disk encryption is ubiquitous, and the purpose of this talk is sort of like, how do we get there with SNARKs and not have it take 25 years? So that's really the goal of this talk, and it's a little bit more forward-looking. We will give some performance numbers today, but it's really about, how do we actually make this practical for large-scale computations? What the talk won't really touch on too much is that there's obviously performance is a combination of both sort of like executing the proof system, but the proof system itself. And there's been a huge amount of improvements in proof systems over the past 6 years. Interestingly enough, Zcash, which is sort of like the first blockchain with SNARKs, was actually launched on this day 6 years ago. Since then, there have been dozens of new protocols with dramatic improvements, and Nova is one of those that is particularly interesting. And there are really a variety of reasons why Nova is interesting. The first is no trusted setup, as Srinath mentioned earlier. Recursion capabilities that allows things like Lurk to exist and to be Turing complete. It has reduced multiscalar multiplication computations, which is one of the predominant sort of arithmetic operations you do when you're generating a SNARK. It runs on 256-bit curves, which themselves are 2 times faster than operating on 384-bit curves. And it has no number theoretic transformations, which is another large component of many proof systems. And so not only do all of these things give you, let's say, a 10x advantage in performance versus other systems, as Srinath had mentioned, or perhaps more, but it actually dramatically simplifies the hardware implementation. And I think, as Srinath mentioned, when you do have this number theoretic transformation, as your circuits get bigger, your memory requirements of the system grow as well. And so by eliminating that, we can reduce the cost and also the complexity of hardware acceleration. Why is hardware acceleration important? Just to level set, this is from a blog post from A16Z just a couple months ago. Their estimate that today, the prover overhead is somewhere between 1 million and 10 million versus native computation. And they sort of give this estimate that, GPUs can buy you a 10x speed up and ASICs can buy you a 10x speed up, and we'll sort of look at how that looks in the Nova proof system. But I think the other important thing is, while they talk about speeding it up, another thing that's really important is how do we reduce the power and the cost of these operations? Because the speed is very important for user experience and other things, but you'll see in some further slides that power and cost will be important factors as well. So just at a very high level, I know Srinath talked a little bit about this, but the main computation that you have to do when generating a Nova proof is something called a multiscalar multiplication. I'll abbreviate it MSM in some of these slides here. It's also called, it's called multi-exponentiation in other places in the literature. And as Srinath talked about, the cost of doing proof generation is 2 MSMs with the size proportional to the circuit. So in the case of Lurk, the circuit is around 20,000 constraints, which means you need to do 2 MSMs of size 20,000 for a total of 40,000 points is what you have to sort of feed into this multiscalar multiplication algorithm. And an interesting thing is, as I think even Chime had mentioned, as the Lurk circuit gets smaller, reduced from 20,000 to 15,000, all that proof generation cost will just be reduced proportionally. And that's not really factored into any of these talks today. The one thing I will also say, though, is that, Lurk, Nova, the underlying proving software, they are still work in progress. They're not fully optimized. And so we'll give you a lay of the land of where things are at today. But there's a lot of room to improve it, is sort of the long and short there. And, there are other functions that have to be done besides multiscalar multiplication, but today that's like 90% of the computation, and so we're gonna focus there, but it should be noted that we can't make just this one function fast to speed up Nova. So what does Lurk performance look like today? So given that you have 40,000 bases that you have to do this multi-exponentiation on, a single CPU core today can do about 100,000 bases per second, which means if you recall the sort of iteration count in Chime's presentation, that means that if you want to do a proof, it's going to take about 1 second for every 2 iterations that are in your thing. And I think maybe some of Chime's examples were perhaps 20,000 iterations or something like that, and so that could take it could take 10,000 seconds. So it's quite expensive today. With a multi-core system like a MacBook, which is what many developers are using, those have 4 performance cores and 4 efficiency cores, and so with that you'll get somewhere closer to maybe 10 iterations per second. And then we actually have a benchmark using the VDF implementation that Srinath had mentioned that actually does evaluates at 2.5 million constraints per second, at least for the VDF circuit, which means that today in Lurk, you can likely do something around 100 iterations per second using a graphics card. So is that the best that we can do with a GPU? So if we are evaluating at 2.5 million constraints per second, that means that the MSM is theoretically running at about 5 million points per second. But we actually know in some pure multiscalar multiplication benchmarks that a modern GPU can actually perform about 125 million points per second on this curve, which means that there's a potential for maybe a 20x improvement over the current software today. And this may involve migrating some of these other smaller functions or that are required for the proof generation to the GPU. And if we are able to do that, we could be in the thousands of iterations per second, which is a dramatic performance from the two on a single core today. The other thing that's really great about multiscalar multiplication being the predominant factor in your proof generation is that the algorithm is highly parallelizable. So if you have to do an MSM of size 1 million, you can split that up and send that to 4 GPUs and each have them do 1/4 of the problem, and then very quickly you can just sort of combine those results. Alternatively, you can use multiple resources on the system. You can send some to the CPU, you can send some to the GPU, or even better yet, we can use multiple graphics cards. And so at a very high level, if you did have 4 graphics cards, it's feasible that we could be doing over 10,000 Lurk iterations per second. Going a little bit further, not only can the MSM algorithm be distributed among resources in a single system, it can actually be sent to resources across many different systems. And by leveraging some of these proof-carrying data characteristics that Srinath talked about, we can actually, send a bunch of different proofs to a bunch of different systems, and then use this sort of PCD binary tree aggregation that will be available in the coming, quarters. To actually dramatically expand where this is at. And so at least at Supranational, we have developed some software that we've actually deployed on up to 2,000 graphics cards at once. And so by deploying that problem across sort of this cloud, It's possible that we could scale Lurk to 5 million iterations per second, or maybe even beyond that. And just as a very high level, you can think about this now as like we have like a 5 megahertz Lurk processor. And maybe even going further than that, in some ways, the Lurk iteration is more powerful than a single CPU cycle that operates on, say, 64 bits. Lurk may be operating on 200 bits or something to that effect. So what's that look like from a cost perspective? We have to really think about the economics of it, the power, what is the capital cost to deploy a system like this. And so I provided just kind of a high-level overview of an 8-core system, just a normal CPU system, the benchmark that we have today, leveraging a single graphics card, a 4-GPU system, and then ultimately the sort of like 2,000 GPU cloud instantiation. And in the far right column, what you'll see here is we have a cost-adjusted performance. And I think a couple of the key metrics that you'll see here is that, today already, the GPU is providing something like a 7x or 10x better cost per dollar when performing the calculation. So not only is it getting faster, it's also getting cheaper to do. As we expand this and put more GPUs into a single system, we're able to sort of amortize the costs of the CPU and the motherboard and the memory and these sorts of things. And so we can actually scale this to potentially about 200 times cheaper than operating this on just a normal MacBook or something to that case. So that's kind of a high-level overview of the cost, but power is another consideration in all of this. And so if you are going to run something like this 2,000 GPU cloud to do all of your Lurk calculations, it's going to consume approximately a half a megawatt of energy. So this is like a massive amount of energy. Maybe in comparison to like a Bitcoin mining farm, it's small, but it's still something that we want to reduce as much as possible. So how do we reduce cost? And the answer from our perspective is with custom hardware. So after we've gone and optimized these off-the-shelf platforms, things like CPUs, GPUs, FPGAs, things that you can just buy on the internet today, the next step is really developing custom silicon. This custom silicon can sort of be instantiated in a couple ways. It could be used as an accelerator that, say, plugs into an existing system. So maybe it plugs into a PCI slot, just like a graphics card. Or it could be more sophisticated and actually be a standalone box that maybe you plug in an Ethernet cable. It's kind of like a Bitcoin miner, and it just generates these proofs for you. But really, the ultimate goal with the Nova proof system is to move all of these functions onto this accelerator. And that includes things like circuit synthesis, witness generation, matrix multiplication, and then a few other smaller operations in the Nova proof system. So what does that look like from performance and power? These are just some high-level estimates. So if that 4-GPU system would cost you $5,000, we expect that this ASIC-based system would cost closer to $500. So we would see something like a 10x lower cost for the same level of performance. And we also would expect that power would be reduced by 10x as well. So ultimately, some of the high-level guidance given in that blog about you'll get 10x better moving from GPU to ASIC, it does turn out to be true here. This is sort of specific to I guess Lurk, but you can kind of think of them as analogous. Yes, those are Lurk iterations. Yep, absolutely. By supporting multiple circuits besides Lurk, you will add some complexity into the prover, and so there is ultimately a decision about how many circuits do you support, how large are these circuits in this custom silicon, and those are some things that ultimately do need to be considered. The other thing, in addition to reducing the cost and increasing the performance and reducing the power, is we can actually have potentially better user experience by developing custom silicon. So the really neat thing about developing ASICs is that you can tailor them for different configurations. So you can imagine that we have a small device that is for a developer that's maybe as powerful or a couple times more powerful than a GPU that they can plug into their laptop or their desktop. But you can also design for a data center. So rather than necessarily having to have 2,000 GPUs, maybe you just have 100 of these boxes plugged into some data center that are generating your proofs. And so you can sort of customize depending on exactly the user experience that you want. And this is sort of a visualization of this. We can imagine that we have some sort of USB-C device that we plug in, and now you're generating your proofs at your 1,000 iterations per second, or whatever that number may be. Or we may actually instantiate this on a server and put maybe dozens of these ASIC chips, or maybe the ASIC chips are much larger, and now this single server may be as powerful as 100 GPUs. So that was kind of a brief walkthrough of where the potential is in accelerating Lurk. We are at in this 100 iteration per second range today. We do think it's feasible to potentially increase that at least up to maybe 1,000 iterations per second on a single GPU. That would be the goal. And this is in terms of level setting expectations. There is a GPU implementation today. So if you go and use Nova, if you use Lurk, there is a GPU flag. And if you have a graphics card in your system, it will detect that and use it. The one caveat is it needs to be an NVIDIA graphics card because that's what the code is written for. Over the coming 6 months, we hope to not only optimize the implementation, but also to enable multi-GPU support. So that way developers can have even faster proofs in their house. And also to extend the GPU cloud that we've been working on so that developers can actually just submit these jobs to us, and we will develop the proof, or run the proving process for them and return them the proof. In terms of the ASIC design and manufacturing, generally that's like a 18-month process, another 6 months of manufacturing and system development. So the first time you would see that would probably be like 2025. So yeah, that's everything I had, but happy to take any questions.
Are you focusing on PLS 12381 specifically because that's what Filecoin uses, or are you looking at other curves as well? So for example, curves with pairing properties or something?
Sure, yeah. So in the case of the GPU accelerated library that we have, it supports a variety of curves. So Nova uses actually the pasta curves today. So the library supports BLS 12381, BLS 12377, the BN curve that's used by Ethereum, the pasta curves. In terms of the ASIC, there's ultimately another sort of trade-off question there about how many curves do you support or what bit size do you support. But sort of anything is possible. But it's just kind of an open question about do you want to take on that complexity. But yeah, the GPU stuff can be used today for a variety of curves.
Thank you.
Yep.
So I have two questions. The first is I was going to ask about the upper bound of parallelization because, of course there should be an upper bound, right? Because otherwise you just, make it more parallelizable until it's like faster than this native sequential algorithm, which is, probably not the case, right? And the other question is if you could use cache for, because, lots of expressions will be shared, right? So in like different programs. So I guess you could like keep a database of like expressions, and hash it, and like, because then you could like evaluate it like really fast using the cache. So.
Yeah, no, those are great questions. So in the first one, in terms of like what is the upper bound, at the end of the day, many of these programs at least need to be executed in a sort of linear sequential fashion natively to generate these witness values. So, it will certainly never go beyond 5 gigahertz or what have you. The other factor there is sort of, how exactly PCD is implemented, how this tree works, how much we can sort of fan it out in the parallelism. But, the really great part about Nova with this PCD is that you can have this sort of scale out type architecture. To your separate or your second question about can we cache these proofs? I mean, absolutely. I think that's really the point of the content addressable things. I don't know if we've given much thought for how to necessarily ingest those because, with the continuation, I believe you have to take some stuff from the previous round. So that's probably more of a question for Chime. But yeah, I think, maybe some of this is possible.
Yeah, right. There's a difficulty with the environment, right, which is dynamic. So maybe
Right. Exactly.
It's a little hard. Yeah.
Yes. But maybe if some of the very first steps are all the same, the first 100 steps, then maybe those could be possibly reused. But ultimately, if you're passing it, you maybe would have to pass in the same witness and all these other things. But I'll let Chime comment on that.
Just to address the concept, I think that the general solution that's kind of easy is to do it at the application level and think of it as having a database that memoizes functions, and then you kind of are just building it up that way. But the more general thing that we definitely have our eye on when Nova gets a little bit further is that we should be, as another kind of folding, with this binary tree IBC, and instead of just allowing sequential things to be made, we can actually probably make it so that the criteria for two things being folded together is arbitrary, and then that will let us have, remember I talked about these RAMs, we'll be able to have an arbitrary merge function of RAMs, and then you could essentially take such a database and take two different universes and slam them together into one and aggregate the proofs as you go.
So it seems to me like if you take something like the Mina protocol, right, where they're using this recursive ZK snarks to roll up the blockchain and you can prove the state of the blockchain very quickly. I mean, if we take this to its logical conclusion, you're kind of doing the work anyway. And you're, and this is kind of ties in nicely to the fact that kind of we're commoditizing this and making it more efficient. Do you think there's a way we could be using this as the proof of work in a blockchain? So, you're doing the work anyway, and now we have an external security budget securing the blockchain rather than these kind of proof of stake systems which are somewhat circular. Do you think there's a there? There's an idea behind that?
Yeah, I mean, I think there's been a couple efforts that are sort of similar and in that vein. There is a company called Alio that tried to make their proof of work generating snarks. The goal of that was not to necessarily do useful work, but to provide incentivization to actually accelerate these systems. In the case of something like Mina, from what I understand, it's mostly an altruistic thing, producing these proofs, though they do have there is potentially a fee market that's supposed to be there, but I don't know that it's fully developed. But I do think, I think it's absolutely possible to reward people for generating these proofs. Many of these proofs, can be watermarked in a way, like you can feed in someone's public key as a witness or something, and then if they publish this on chain, then they can potentially be rewarded. So yeah, I absolutely think that, we will see in the future that people producing zero-knowledge proofs will be rewarded in some way.
It's a bit of a joint question because it's also partially answered. With this tree IB,
the PCD?
IPC, yeah. When you said aggregating proofs, does that imply that the parallelization of sub-proofs are themselves proofs? So you could meaningfully over network decentralize the proof aggregation, or is it a trusted entity?
Yeah, so I think in the case of this binary tree PCD, you would sort of complete, all of these leaves could potentially be done in a decentralized way by independent provers and independent data centers, and then have some orchestration layer to ultimately aggregate these into a single proof.
Very nice.
I have a question from the live stream, folks.
Sure.
The CPU ASIC/GPU comparison, including wattage, is very insightful. Thank you. Have you experimented with FPGAs, and do you have a ballpark of where that would stand in the trade-off space?
We have not implemented the multiscalar multiplication algorithm on an FPGA. However, there are a few recent papers that do so. My understanding, just at a very high level, is that if we look at this on the GPU, we're getting roughly 100 million multiscalar points per second. My understanding of the FPGA is that it provides lower power, but is closer to being on the order of, let's say, 5 or 10 million. So I think in general, it's been sort of our thesis as a company that multiscalar multiplication is not an algorithm that is going to provide, is the best fit for FPGA or going to provide the best cost per operation. And that's been our take, and which is why we've chosen the GPU path.
Thanks. Sorry, I want to ask a dumb clarifying question. First, two parts. First, is PCB kind of like Blake 3ing the Merkle-Damgard looking thing from the Nova talk?
Yes, it was the thing that was sort of a tree of proofs coming together. I think maybe even Srinath had given a talk, Chime had given a talk where he said IVC is sort of linking one proof to one proof to one proof.
Yeah.
PCD is sort of where you're doing a bunch of proofs in parallel and then sort of rolling them up into a Merkle tree type thing.
Awesome. Second question with that, is the ordering of the proofs within that tree, is that arbitrary, or does that have to go along some line of the way that the Lisp syntax, does it have to align with that AST at all, or can it be arbitrary?
I think it does have to be sort of ordered at the leaf layer. I'm probably not the
Well, yeah,
person
ordered for verification, but does it have to have any kind of correspondence with the Lurk AST? Or can it be kind of put into the tree and some other order?
My guess of how this would work is that iterations 1 to 100 would be one proof, iterations 101 to 200 would be the next proof. And so you would compute, you'd run through all the iterations sort of natively, and then you would start doing these proofs, for each 100 iterations in separate leaves of that tree. And so they would sort of be ordered, but could be computed in parallel.
Okay.
So yeah, sort of getting back to the question, you do have to do some level of sequential operations first, such that you can generate all these proofs in parallel.
Awesome. Thank you so much. So it would just be the combination step that happens second. Okay. Thank you.
Exactly.
How do you think about, I guess, committing to an ASIC design and the timeline for that versus, I guess, the kind of fast iteration rate of new proving systems?
Oh yeah, I think the question it cut out a little bit, but I think the question is how do you decide whether to commit to an ASIC when maybe a proving system will come out next week that is 10 times faster than Nova? I think it's a relevant question. Ultimately, our view is that an ASIC makes sense when the compute gets large enough to warrant cost reduction. So if we have 5 Nova proofs being produced per day, we should probably just use a single GPU to generate all those proofs. So I think for us, it's really more of an economics question. If we get to a point where we are generating millions of Lurk proofs per day, then the investment is warranted. So there's a bit of a timing question there. Fortunately, from a development standpoint, many of these core algorithms are the same across proof systems. So they use almost every proof system, apart from Stark's, uses multiscalar multiplication. So if we were, the work in the ASIC development can be reusable for other proof systems.
First, thank you for the talk. Packed full of unusually useful information. If I could ask one Philistine question, I've spoken to a number of companies that take a different IP approach for each hardware implementation, like hardware acceleration that they're doing. Have you guys given any thought to that, like what your IP strategy is now and whether that's going to change for the GPUs versus for the ASICs?
Yeah, I mean, today, everything is basically open source. The GPU implementation is open sourced. For the VDF hardware we're building, the core sort of function of that called minroot is open sourced. It's our goal to open source as much as possible, but there is ultimately, there are economic questions about these things. So I think there's questions about the timing of the open source. But our goal is to make this stuff as available as possible to benefit the community.
So when you say timing of the open source, like you might go into production using a different license and then open source it later, or
Or it could
won't
be that
open
you
source
wait
it
till the
until-
chips are actually, you know, going into the factory or coming out of the factory before it's open source, or maybe you wait 1 year so that you get a year of sales before someone knocks off the design or something like that.
Thank you.
Yeah.
Any other questions?
Do you guys have talks out on the VDF hardware?
We don't have any talks out. Actually, I mean, there are some sort of older ones, but no, not currently. If you do go to, you know, github.com/supranational, the hardware is the hardware implementation is there. If you read a paper called, I believe it's called Not So Sloth or something like that, it's by the Ethereum Foundation. I believe it's Dmitry Kovatovich. He documents the actual algorithm that we're using, and those are kind of the core components. But yeah, we don't have any talks on the hardware yet. We are expecting that back in either late December or early January, so that's when we're actually going to get it back from the fab and power it on and that sort of stuff. So I anticipate that in the next quarter or so, we will, you know, start to release some information on it.
All right. Thanks, Kelly.